for the talk of the day, talking about AsterX. So yeah, please take it away.
Well, thanks a lot. Thank you, everyone. So very happy to connect with you all here. I thank the organizers for giving me this opportunity. And today I'll be talking a bit about our new GRMHD code called AsterX, which is based on the CarpetX framework. This code has been developed in collaboration with many people that you might see listed here: Federico Armengol, Steve, Manuela Campanelli, Riccardo Ciolfi, Lorenzo Nocci, Bruno Giacomazzo, Roland Haas, Li Wei Ji, Lucas, Timoteo Sanchez, Eric Schneider, Johnny Sao, as well as Josef Zlotchauer. So to give you a brief overview of for the next hour, I will start with a brief numerical background, maybe a few slides. This is basically catered for people who are new to GRMHD, and then just describe a very rough code workflow, and then jump on to some details of our AsterX code and describe the test results as well as the performance benchmarks. And the second half of this hour, we will spend some time on hands-on tutorial. And for this, Leeway in the audience kindly agreed to do this in person because he's there with you all. So we thought it might be better that he can guide you directly in person. So needless to say, to model different astrophysical scenarios and understand the underlying physical mechanisms, such as for scenarios such as binary neutron star mergers, proto-neutron stars, supermassive binary black hole mergers, accretion disks around the black holes, as well as these relativistic jets. GRMHD simulations, or the so-called general relativistic magneto-hydrodynamic simulations, play a fundamental role. And so in order to perform these simulations, we need numerical relativity. That's why we are all here. And the standard approach that most of the codes that follow is this 3+1 technique has been extensively talked about. So typically, for spacetime evolution, which is based on BSSN or Z4C or your favorite formulation, there are thorns in the Einstein toolkit, such as McLaughlin, Bicol, Z4C, etc. And for GRMHD evolution, which are typically based on these Valentia formulations, we also have different state-of-the-art codes such as Whiskey MHD, Illinois GRMHD, GR Hydro, Spritz. And earlier on Tuesday, you also heard from Sam about Greyhole. That is this new library also catered for Einstein Toolkit. Or any other infrastructure, in fact. Sorry about that. So for the Valentia formulation, the GRMHD equations are formulated as a set of first-order flux-conservative hyperbolic equations of this form, where you have U as the state vector, and F here stands for the fluxes, and S are the source terms. So this might feel like a lot, but just to give you a brief idea that essentially these are the different variables that are actually evolved in the code. And these are the fluxes that are computed typically at the flux cell faces. And then these are the source terms, which are when they're non-zero, this means essentially that the fluid can interchange energy and momentum with the space-time. And these are essentially conservative equations, like I mentioned earlier. So typically, the primitive variables that you have in the code are defined such as rest mass density, fluid free velocity, specific internal energy, also electron fraction. And using these primitives, you can, through an analytical expressions shown here, you can define a conserved variables such as the conserved density, momentum, conserved internal energy, tau, magnetic field, as well as electron fraction. So these we typically call as conserved variables. And typically, most GRMHD codes are assume work under the assumption of idle MHD, which essentially considers perfectly conducting fluid, and also assumes that the co-moving observer in this case measures no electric field. So the Maxwell equations can then be recast solely in terms of B, small b, as written here. And this can be broken down into the divergence-free condition as well as the induction equations for B here. And the co-moving magnetic field components are also shown here in terms of the big B or the Eulerian B. Some codes might choose to evolve instead the vector potential and compute B from the curl of this vector potential. And also one has to make some gate choices in evolving these induction equations for A. And in literature, you might find the simplest one choice to be the algebraic gauge. But the more commonly used one is this generalized Lorentz gauge, where in this case, you also need to evolve an additional equation for the scalar potential 5 here. So I'm not going much into details. Also, to close the system of equations, you need to provide an equation of state. So typically, the simplest forms assume this analytical expression. For example, this is the ideal gas equation of state or a polytropic equation of state. One can also choose to combine these two. So in terms of columns, like we call them as a hybrid equation of state, where you have the cold polytropic part as well as a thermal component. Some codes also would use a tabulated equation of state, could be one parameter or even more complicated composition temperature dependent 3-parameter equation of state, especially to simulate neutron stars. Now, modern codes also employ something called as high-resolution shock capturing techniques in order to accurately capture the physics at shocks and discontinuities that one might encounter also in different astrophysical scenarios. And for this, we have two main components. One is reconstruction, and which basically involves reconstructing the primitive variables at the grid faces. And some of these schemes, different schemes have like, this is include like min-mod reconstruction scheme or a piecewise parabolic method. And then once you have reconstructed your primitives at the cell faces, then you can compute the fluxes there. And there are different approximate Riemann solvers to do this, such as Lax-Frederick solver or HLLE solver. And just on the right, I just show a typical diagram where you have, if you have your grid variable at the cell centered, and you might want to reconstruct it. This is a simple Leland extrapolation to either the left or the right side of the grid cell, and then you produce this discontinuity or a Riemann problem, and that can be then solved using these Riemann solvers. Another core element of a GRMHD code is a contour prim, which essentially stands for conservative to primitive variable recovery. And as I mentioned earlier, you have this prim to con step where you have analytical expressions that can compute conserved variables from the primitive ones. But in GRMHD, there is no analytical solution when you want to do the reverse. If you want to compute the primitives from the evolved variables, the evolved conserved. So one needs to employ numerical techniques, root finding algorithms, essentially. And there are many different kinds of these contour prim schemes that exist in literature. Typically, some of them are based on Newton-Raphson schemes, and the other might employ root bracketing schemes. So these are some of the elements that a GRMHD code might entail. Just to give you a quick recap of how things are all put together. just a reminder then again that we are trying to solve this kind of equation in the flux conservative form. So the first step is to initialize your primitive variables at time equals to 0 at each grid point in your simulation. Then you do a prim to con to compute your conserved variables from the primitive ones that you just defined before. And then the next step would be to compute the source sums that I showed earlier using finite difference schemes. And then you employ these high resolution shock capturing methods to compute the flux terms at the self interfaces. And then flux minus source terms would give you an ODE that one can then solve using time integrators such as Runge-Kutta 4. And the last step would be to do prim to con to compute your primitives from the evaluated conservatives from the next time step. And you can then keep this on a loop until you arrive at the solution that you desire for your system. So that was a very quick introduction. So jumping on now for one of the frameworks that we use is something called as AsterX. And I think Eric mentioned earlier, on Tuesday, this is software framework for massively parallel block structure AMR applications, and it's been developed as a part of DOE's exascale computing project. And some of the key features that it allows is this. Apart from this block structured AMR, it also allows for support, for instance, for cell-centered, face-centered, vertex-centered, edge-centered variables. It also has support for particles that might be interesting if people want to do some kind of like Monte Carlo simulations and things like that, or PIC simulations maybe. And more important part is that performance portability. It is compatible with different kinds of architectures when you want to on CPUs as well, if you want to do MPI or a hybrid MPI OpenMP, or also on GPU architectures employing CUDA or HIP with CUDA or HIP Axel compilers. So on top of AsterX, we have CarpetX, as you might have heard from Eric's talk on Tuesday. And again, the fundamental, this is a new driver for Einstein Toolkit, and which provides also supports for accelerators through essentially GPUs. And some of the interesting components include support for refluxing. Also, you also can do some AMR based on your local criteria that you can that can be user defined. And some of the this development is publicly available on GitHub if anybody would like to check it out. And some of the applications include evolving simple wave toy. Also, there is a spacetime solver based on the Z4C formulation. And there is also another GRMHD code called GRMX, which is developed by Swapnil Shankar, Philip Mosta, and the group in Europe, which also takes advantage of CarpetX. So another GRMHD code on the list is AsterX, which also is based on this CarpetX infrastructure. And AsterX is based on this previous parent. It's called the Spritz code. And Spritz, we evolved the vector potential for magnetic to compute the magnetic and then compute the magnetic field. So on the right, you might is a typical grid cell where I show locations of these different grid variables, especially the magnetic fields. So here, the vector potential is stored in a staggered way where it lives on the edges. For example, if you take one face here on the top, you have the AX and the AY components living on these edges. And then if you take the curl, you would automatically get the B component along this face, which is the Z component. So this has using staggered formalism has proven advantageous to deal with shocks and other problems. So this is what we adopt. Now, to summarize some of the modules that are present in AsterX, the first one is a ReconX that essentially is a provider for different reconstruction schemes, just like MinMod, PPM, or even Reno-Z and MP5. Then we have the flux solvers, the simple ones, Lax-Fredericks and HLLE, but we plan to include HLLD too in the future. There is another module or Thorn called Contoprim Factory, where we provide two contoprims based on 2D Noble and 1D Palenzuela et al. We also have coupled the Reprimand library, but this is currently only CPU friendly. So we are on the way of porting that to GPUs as well, and also try to include other contoprims as well in this module. Next is the EOS support. For that, we have the EOSX Torrent. And currently, we have only support for analytical equations of state. But we have started implementing support for finite temperature tabular equation of state as well as the hybrid ones. For vector potential evolution, we have the possibility to compute the electric field in the flux CT approach or the more correct up-in CT approach, and we've implemented both of that and tested, and seems to work great. And all the development for AsterX is also publicly available. If you want to check it out, it's on GitHub. But now let me move on to some of the results some of the tests that we performed with AsterX, starting with the simple shock tube test. So this is the test suite of Balsara shock tubes, where we compare our results with the exact solution. So on the left panels are for density, on the right panels are for the Y component of the magnetic field. And we see that at the final time of these simulations, they seem to match well with the exact solution. Next was to study if our code is actually converging at least to a second order. So we repeated the tests. We performed this alpha waves test where you advect an alpha wave across the domain using periodic boundary conditions, and after a few periods, you can actually check the differences between the initial data, and as you increase the resolution as number of points, you should see if your code is actually converging at least to a second order or not. So this is what we did, and we see that it does converge to second order at least. And of course, we want to extend this to higher order as well, so that would be something to be done in the future. And next, we move on to 2D tests. So this is where you see a cylindrical explosion is a standard test that is performed. And we find that these profiles for rest mass density, magnetic field, and other such profiles do match well with what's been reported in literature. And similarly, we have the magnetic rotors test, where you have the cylinder fastly rotating in an ambient medium when it's magnetized. And again, here the profiles look quite similar to what's been reported in the literature as well. The third one is, again, a loop advection test. This also checks if the code works well with the periodic boundary conditions. So here you see that the loop, a magnetized loop, is being advected across the domain, and it seems to perform well too. The next 2D tests was to also play a little bit with this block structure AMR, which is dynamic in nature. And we tried to play with these refinement criterion, according to which you might try to refine some of the interesting physics that is going on here. So this is done based on this Kelvin-Helmholtz instability test, where you have, which is essentially a fluid instability that develops in shear flows, and can when you have differences in velocities, for instance, at these shear layers. And for this, we also find that, to give you a better picture here, that we are able to, this is just like refine across these the shear layers of the vortices that are developed here. Next, we tried the magnetized TOB tests in cowling as well as in full GR, also evolving spacetime. And on the left is you have the rest mass density evolution, and on the right you have the X component of the magnetic field. And the idea is to have the star as stable as possible, but you might see that there might be some oscillations induced. This is because of the truncation error when you actually start to impose the initial data on a 3D grid. And this would lead to some kind of radial oscillations. So in terms of checking the evolution of maximum of rest mass density, on the left you see this. We tried the simulation with different resolutions, and with increase in resolution, our results seem to converge. And essentially, these oscillations are a bit more damped with increase in resolution, as well as there is no damping of the solution itself. And we then checked the power. We then did the Fourier transform of this rest mass density and the maximum rest mass density, and this essentially tries to find if what are these oscillation modes because of this truncation error that I talked about earlier. And we compare this with the perturbative code that also can reproduce these oscillations. And we find that the oscillation frequencies are matched quite well, especially even up to 4th harmonic when we go to high resolution. After that, we did some performance benchmarks, and here basically on 3 different setups. This is all based on the magnetized TOV simulation I showed earlier. First with, again, calling spacetime in a uniform grid, then a dynamic spacetime evolved via the Z4C Thorn, and again on a uniform grid, and the third one considers instant 8-level box-in-box AMR structure. So on the right, you see the results for the strong scaling test. Here we keep a fixed problem size and try to increase the number of GPUs on this frontier. And as we increase the number of GPUs, you might see that the efficiency goes down. Sorry, I forgot to mention that we measure performance in terms of zone cycles per second, or basically average grid cell updates per second. Yeah, so I think with about 1,000 GPUs, the strong scaling efficiency goes down to about 50% compared to an 8-node performance, and it goes down to about 20% for when we go to about 8,000 GPUs. Instead, for weak scaling, we find we do the same. We keep the same problem size per GPU. So we set either 128 cube per cells per GPU or 240 cube per cells per GPU. Again, for these 3 setups that I mentioned earlier. And one trend we see is that for the setups with high computational load per GPU, the absolute performance is slightly better. It's essentially because you're trying to use the GPUs as efficiently as possible. And the second trend we find is that typically the scaling stays to about 85 to 90% about 1,000 GPUs or more, but then it goes down to about 70 to 80% for setup A, 60 to even 23% for setup B that involves spacetime evolution, and about 20 to 30% for setup C, which has AMR. So definitely inter-node communications and synchronizations can lead to this decrease in performance. There's also, you have another feature called subcycling in time, and the Leeway talked about this in great detail in this talk on Tuesday. So we've tested it with AsterX as well, and we definitely find at least a factor of 3 to 5 times increase in performance when we simulate the exact same system activating subcycling versus with simulations which do not have subcycling in time. Next, we also try to profile our code to understand if you're using the GPUs efficiently or not, or if there is a lot of memory transfer or not. So we indeed see that this is done through NVIDIA Insight system. So we indeed see that the blue here basically means you're using the GPUs, while the red is essentially for memory transfer, and the black denotes the CPU workload. So when our kernels are evolving, they're essentially more or less working with the GPUs here. So that's a good signature. Next, we also try to profile the code using the HPC toolkit on Frontier. Again, this is another way to understand how different kernels are behaving. For instance, we find for AsterX, this was again a magnetized TOV with encowling. So just to see how the different AsterX kernels are behaving, we find that the flux is to be consuming about 60 to 65% of the total compute time. Of course, these are expensive because this involves reconstruction as well as and the Riemann solvers for 3 directions, X, Y, and Z, 3 faces essentially. And next was computation of source terms, and also counterprim take to about 10 to 15% in that case. We also, for ongoing developments, we have a postdoc at RIT, Mikhail Shabana, who is currently implementing the photon linkage in AsterX and trying to perform some FMDIS simulations that you see here. This is still a work in progress. And meanwhile, I'm trying to perform some DNS simulations as well with the help of using Fuka initial data, as well as the importer was provided by Samuel Tudor. This is again something ongoing as well. So essentially, AsterX is currently a work in progress. The code is being developed still. We are extending these EOSX and Contoprim factory torrents. Next thing we want to look at is how to optimize, especially this flux computation kernel, and also implement M1 transport scheme. With that, I stop here and would be happy to take any questions. And also, we move to the second part of the tutorial where Liwei would like to would do some hands-on with it. Yeah, thank you very much.
Okay, while Vijay gets set up, why don't we talk about questions? Anyone have any questions? No, really? Okay, well, I'll ask one, Ken. So, you discussed some of the components like the Contoprim factory and the EOSX. What has your experience been as far as implementing those capabilities on device? Were there any gotchas that you got hit by that might be useful for people following in your footsteps?
Right, I think the most, I'm now trying to understand how to have the tables to be read using, I think, this shared memory or on different clusters, like, for example, Frontier. So we want to make sure that we are able to read, there's a different possibilities for memory for memory allocation on provided by AsterX. So I think that's one thing that we are trying to see is how to efficiently load these tables that can be shared between the different made available on GPUs. I think that's one bottleneck that I'm still working on. In terms of Contoprim, I think we want the reprimand in there. I've almost ported most of the components. It's just that, yeah, it's a matter of time.
Yes. So, given that Kalinani just gave us a presentation where he went into a bit of detail about register pressure on the GPU memory usage, do you have any information how well AsterX is faring in that respect?
Memory usage? Good point. I think that I would have to check, I think, the profiling more in detail. Maybe that would where I could see this memory usage, or yeah, I haven't looked into it in much detail.
Yes, there's a question online.
Oh, okay.
I suppose you can just read it yourself.
Right, so I'm just reading it. You mentioned including HLLD in the future. Are you planning to perform a frame transformation to a locally Minkowski frame like Athena++? If so, do you expect any difficulties doing this in dynamical space-time? Right, so we haven't thought much on this yet. This is probably a bullet point for future work. Yeah, once we get there, probably we will think a bit more about the implementation. Yeah, I don't have much on that. Sorry. But yeah, we are able to evolve in general with magnetic fields with HLLE without problems. So I don't foresee any major difficulties also with HLLD. I know that HLLD is a bit less dissipative, and that's why we want it there. But at the same time, it's also, what I've heard is that it's also prone to, it's unstable. So sometimes it can, so at that point, we can, I think, fall back to lag spread rigs or things like that. So yeah, not much has been given thought on that yet.
There'll be more time for questions after the tutorial. So let's thank Vijay again.
Thank you.